The next presentation of today will be with Sercan Arik, highlights from pushing state-of-the-art AI into the world. Sercan, thank you so much for being with us today.
Thanks for the introduction and thanks for the invite. Hi everyone, I'm Sercan Arik. I'm from Google Cloud AI Research. In general, Google Cloud is focusing on bringing AI technologies to different industries, and our research group is focusing on the high-value research problems that are motivated by this mission. And today, I'll overview some of the projects that we worked on recently. I'll first start with tabular data, TabNet for improving the tabular data learning with deep neural networks. So tabular data is one of the most common type in the addressable AI market. We see a wide range of applications of it in healthcare, finance, retail, energy, and so on. And canonical deep neural network architectures for tabular data have been underexplored. Still, majority of the solutions are dominated by variants of ensemble decision trees. In this project, our goal was to explore deep learning for tabular data and push the state of the art in accuracy while also preserving the interpretable capabilities that are motivated by the needs of some of these applications. Why deep learning? There are a few fundamental advantages of deep learning. It has potential for better scaling with larger data sets. It can efficiently encode multiple data types like images or text along with tabular data. It can alleviate the need of future engineering, so there would be less reliance on the data scientist. It can enable end-to-end representation learning, which might unlock new capabilities such as semi-supervised learning or data-efficient domain adaptation. It can have some benefits for learning from streaming data. For this TabNet architecture, we propose a novel attention mechanism, which is based on sequential decision-making. So the high-level idea is shown here. Given that we have a bunch of numerical and categorical features, at each decision step, the architecture looks at the features and decides which ones to pick for that decision step. Then those are selected and then processed, and the information is transferred to the next decision step. TabNet architecture inputs raw tabular data and it's trained with end-to-end learning, and it provides two types of interpretability. The local one, which shows for each sample which features are the important ones for decision making, and also the global one, which is showing the global contribution across all the samples of each feature. We have demonstrated TabNet on a wide range of public data sets, and we have shown its outperformance compared to commonly used both deep neural network and other popular tabular data learning methods. An interpretable capability of TabNet is highly interesting. So there are a few examples shown here. On the left, we are seeing the instance-wise feature importance capability of TabNet. And for this data set of income classification, the model can correctly identify important factors like education and occupation and so on. On the right, we have a synthetic example, which is showing that TabNet can correctly identify the ground truth factors that determine the input-output mapping. Lastly, we have also demonstrated the self-supervised learning capability of TabNet, which can be very important to benefit from large amount of unlabeled data sets. So the high-level idea is that when we don't have the labels for the data, we can still propose a self-supervised learning objective. And in the form of unsupervised pre-training, the model learns the structure in the data. Like for this simple example, if we mask some columns intentionally, for example, if the education is masked for a row, the model can figure out from the occupation what the education of that individual should be and so on. So by figuring out this structure in the data in an unsupervised way, then efficient supervised fine-tuning can be enabled with very small amount of labeled data. And we have shown the benefits of TabNet in this semi-supervised learning scenario. The next project I will describe is for time series forecasting using temporal vision transformer architecture that we propose. Similar to tabular data, time series forecasting is also one of the most common enterprise AI use cases, and it occurs commonly in finance, energy, healthcare, and so on. There are a wide range of challenges for time series datasets. One of them is real-world time series datasets consist many different types of input features. So there are some past observed inputs, which might be past sales. There are prior known future inputs, which might be holiday dates or planned promotions. There are static features, which are store locations. And these all change the time series dynamics in complex ways. Typically, only a subset of these input features are relevant, and the remainder is noise. And deep learning can be prone to overfitting, so it's important to not to fit to spurious patterns and extract the information in an intelligent way. Typically, we are predicting multiple time steps into the future, which we call as multi-horizon forecasting. And there is increasing uncertainty into the future, and it's desired to model that because for various applications such as retail planning and so on, we need to know the amount of uncertainty for certain predictions into the future. There are different types of dynamics in real world. There are some seasonal effects, there are some events that change the dynamics, and there are some transit cooldown periods, decays, and so on. And different architectures are capable of capturing different dynamics. And in this architecture, our goal is to address these wide range of use cases in a canonical way. And interpretability is also very important for time series forecasting. So the users need to know why certain forecasts are made so that they can use those insights in their actions. In the design principles of the temporal vision transformers, TFT, we have certain goals. So we want to propose end-to-end learning. We want to obtain high performance in wide range of dataset regimes. And we want to enable both time-dependent and static interpretability. There are multiple principles we adapt. So TFT is based on recurrent layer space and also attention layer based sequential processing, because recurrent layers are typically more powerful for capturing local dynamics, whereas attention layers are typically more powerful in capturing the long-term context and distant past. Then we propose separate processing for past observed and prior known future sequences. We propose integration of static features to condition the sequential learning. We propose variable selection for time-varying covariates and adaptive depth and complexity to cover the wide range of dataset regimes. Here is the architecture of TFT. So it integrates sequence modeling to capture information from past inputs and known future inputs, followed by a novel attention mechanism that we propose for interpretability. And you can see that there are different mechanisms such as adaptive depth and conditioning on static features to further push for the performance. On some important public benchmarks, we have shown significant outperformance of the proposed TFT architecture compared to some of the traditional time series methods like ARIMA and exponential smoothing and so on, as well as some of the more recently proposed deep learning architectures. And besides accuracy, interpretability capabilities are also quite interesting for TFT. So I will demonstrate a few of them. Variable importance is one of the commonly used ones. And for this example of the retail forecasting task, we can see that the model figures out that features like the past sales or the holiday dates are the most important ones. Another one is discovering persistent temporal patterns. So on these traffic data sets that we focused on, the model from scratch learns these attention patterns which show which time steps in the past are the important ones. And we see that those are separated by roughly 24-hour peaks, 24-hour periods. And we know that intuitively this makes sense because traffic patterns repeat daily. And here the model discovers this from data from scratch, which is important to build trust for someone who has insights about this application area. And lastly, another interpretability use case is in-sample regime identification. And here we show this on volatility prediction task. So we know what kind of what attention patterns the model focuses on while making the predictions. And if we quantify the deviations on these attention patterns, then we can figure out whether there are some important regime changes in the data. And if we focus on the volatility data set, we observe that typically these regime changes correspond to the financial crisis periods. And it's also aligned with the domain knowledge for this data set. Next, I will present our work on responsible AI, learning deep learning models that can be controlled with rules. In practice, there are many rules that contain very valuable information for artificial intelligence. So there are equations, regular expressions, monotonicity constraints, fairness constraints, and many others depending on the application area. And when we consider the standard way of applying machine learning, there is only data-driven learning. So typically the prior knowledge in these rules is discarded. And it can be actually very valuable depending on the application. Here we have this motivating example from physics. So we have this physical system of double pendulums. And here the rule is energy conservation principle. So we know that the energy should not be increasing in the system. And we create a task by generating a data set to predict the input-output mapping by learning from it. And we show that even if we have good amount of data, typical black box machine learning models cannot always satisfy this energy conservation principle. We need to specifically teach this energy conservation principle to this machine learning model so that it learns how to satisfy it while accurately predicting the next step. And as you can imagine, there might be many other cases that such rules can have very valuable content, such as in finance or such as in healthcare and so on. So we need a systematic framework where learning from rules is enabled, and also the users can adjust the strength of the rules at prediction time so that we have the appropriate strength that enables both satisfaction of the rule with sufficient ratio as well as accurate predictions. We propose a novel architecture to enable this, and our high-level idea is based on integrating a rule encoder besides a data encoder in deep neural network architecture and creating these two pathways between input and output and supervising learning with an additional rule-based objective. And here, the rule encoder and data encoder outputs are combined in a way that is controlled by this coefficient that we propose. And this coefficient is also coupled in the definition of the loss function during training. And at testing time, we can also control the value of this coefficient, and it allows us to control the amount of contribution coming from the rule encoder versus the amount of contribution coming from the data encoder. And this can be used for different applications that I'll describe next. So there are different cases we focused on with this idea. So one of them is teaching the known rules that are correct 100% of the time. And energy conservation is one example that we know that energy conservation rule should be correct 100% of the time. But we don't want the rule learning to dominate arbitrarily high, because then the value of past data might decay. So there's typically an intermediate point where the rule learning should be increased to, and that intermediate point typically gives the best accuracy. And the first plot here shows that. So when we consider a very low value of alpha, typically the rule strength parameter, typically the error is high, and as we increase it, the error decreases, but beyond some point, error increases again. And the rule verification ratio, in other words, how much this energy conservation rule is satisfied, it increases as we increase the rule control parameter. So here, the optimal value of error is at an intermediate value. And actually, at that point, we significantly outperform only data-driven learning. Another example we considered is a real-world application from retail. So in retail, there are certain rules that are derived from economical or other business principles. And these rules are not correct 100% of the time, typically. And here we focused on the rule of price elasticity of demand. At a very brief level, this rule suggests that if we increase the prices of certain goods, its sales should decrease. But this rule is not correct 100% of the time, like especially for luxury items or some other specific products, this price elasticity of demand is not valid. So we want the rule learning system to identify that and give us the capability to actually test this hypothesis so that for different products, we can adjust the rule strength and the accurate predictions can then be made. And here we have these three different subsets of products, and we see that the optimal value of the rule strength is different for different product categories, and it gives insights about each product category satisfy this price elasticity of demand principle. Then we considered this example from healthcare on cardiovascular disease prediction. And here we find a rule that attributes cardiovascular disease to a certain risk factor of an individual. And this rule is, again, not correct 100% of the time, but it is consistent with the healthcare literature. So it's known to be true most of the time. And we split the data into different categories based on this risk factor. And each individual's in these categories have similar characteristics in this risk factor. And we show that if we train a model in one subset, which is different in characteristics in this risk factor, then we can adapt this model to these different other subsets that are distinct in this risk factor by adjusting the rule strength. And the optimal amount of rule strength, again, depends on how much that risk factor is prominent in that category of people. Next, I will describe our project on data evaluation for robust learning and interpretation. Naive application of machine learning considers all data samples equally, but we know that in most of the applications, there's a wide variance of value of different data samples. So sometimes individual data samples might correspond to different time periods, different locations, different types of individual stores, and so on. And we want to prioritize the more valuable data samples highly in the machine learning system and deprioritize the less valuable, less relevant ones so that the model performance can be improved, it can be more robust, and also we can get better insights about data collection processes. In this project, we propose a reinforcement learning-based data evaluation system. And the high-level idea is that besides a predictor, we also propose integration of data value estimator in this machine learning system. And the data value estimator basically looks at the data and estimates the value of each of the samples. And these estimates are then used for training of the predictor. So if some samples are higher in value, then they are prioritized more in the training of the predictor. And if some samples are low in value, then they are deprioritized for training of the predictor. And we have a reinforcement learning-based system for guiding of the data value estimator. And here we have the reward for reinforcement learning coming from the prediction on some validation performance. And this reward guides the training of the data value estimator. And eventually, as the model converges, the data value estimator becomes more and more accurate in attributing different data values to different samples. And the predictor also gets more and more accurate to better take advantage of the valuable data samples so that the accuracy improves more and more. Here is the high-level formulation that I'm not going to details, but basically this is a fundamental non-differentiable problem with bi-level optimization, and that's why we adapt reinforcement learning, which is a common practice when we have non-differentiable objectives and we have a way of interacting with the system and getting a reward from it. We have demonstrated different use cases of data evaluation, and one of the important ones is robust learning with noisy labels. So if there are some noisy labels in the data set, then we don't want such noisy labels to dominate learning. We want to assign lower values to noisy samples and higher values to clean or high quality samples. And here we demonstrate our methods for this use case, and we show that our method can outperform the state-of-the-art methods for noise-robust learning, which are typically based on some form of meta-learning. And as you can see, the improvement compared to baseline in this case can be very significant. Another important use case is domain adaptation, and it occurs in real world in many different ways. For example, there might be time dependence in the data set, and because of the non-stationary effects, more recent data might be more valuable than the past data, or there might be different store types for a retailer, and some big store types might be more relevant for a big store than small stores and so on. And the use cases we focus on here are, we have source data sets that are typically lower quality or less relevant to the target task. For example, for skin lesion classification, the source data is the crowdsourced data from web, and the target data is high quality clinical data. And obviously, because of this distribution mismatch, the models trained only on the source data might get quite low accuracy. So we need to figure out which samples from the source data might be more valuable to focus on that are more relevant to the target data. And we show that by adapting our methods, we can get very significant improvements in accuracy. Another one is source is synthetic data set, and the target is a real data set. Another one is source is this email for spam classification, whereas target is SMS for spam classification. And you can see that across these wide range of cases, we can show significant improvements compared to the baseline. Yeah, it is all I have. I would be happy to answer your questions. And I would like to end with the conclusion, with also the announcement that our team is growing in Budapest, and we have a wide range of roles available. So if you are interested in them, you can check this link, or you can also contact me. And if you have any questions about my presentation, I would be happy to take them in the remaining time.
Hey, Sercan, thank you for your presentation. It's very interesting to hear from you from Budapest as well. And I'm quite close to Google ground. So let's say we have a pretty good connection there. One question from the audience that I would like to address to you is that AI-based technology is very much for the use for healthcare services. How about the regulations of these devices? Has the USDFA given draft guidance with how to apply to other agencies? What is your take on that?
Yeah, so it depends on the application area. Obviously, some of the application areas can be much more sensitive to regulations, like especially in finance and healthcare. There are a lot more regulatory rules on AI. And typically when we develop an application for those industries, we need to consider those regulation constraints. Data privacy might be one important one. So we might have limited access on how we use the training data, or what kind of operations we can do on sensitive data and stuff like that. Or fairness can be another one. So you might need to make sure that the model is explainable and it satisfies some fairness constraints expected from the regulators or the customers and so on. So typically it is very application dependent, and we have to adapt our methods to satisfy all these regulatory constraints. And yeah, it might also be country dependent, I guess, like US might have different regulations or rules about some of these AI methods compared to other countries. And that's also typically taken into account as we productionize some of these solutions.
Yeah, very clear. How do you see, perhaps that's a bit of a question from my side. What is your view on the ethical side of AI from a Google perspective? Can you give us some insight? Like, where do you see the opportunities and where do you see the dangers?
Yeah, so I think that it's definitely very important to develop AI in a responsible way. And at Google, we have AI principles that overviews like what kind of ethical considerations we take into account as we develop AI models in research and development, and also as we deploy them. And it's very important to understand the different ethical consequences of the models we develop and what kind of impacts they can make. And I think that it also opens a lot of room for further research, because currently state-of-the-art deep learning is typically not very explainable and not very controllable. And as you saw in my presentation, we had a bunch of works on how to make deep learning both high performance and also explainable and controllable. And these aspects can be very important to satisfy some fairness requirements so that the users or the authorities can understand how the model is making certain decisions and they are fair. And also we can take actions on modify the model learning so that it can be more fair. I believe that this area is open to a lot of room for improvement, and hopefully as AI satisfies more and more of these concerns, it will also be deployed more and more widespread.
Yeah, so it will be a commodity instead of being limited. One question from the audience. What are some of the high-value applications for TabNet and TFT?
Yeah, for TabNet and TFT, as I mentioned, tabular data and time series data are among the most common use cases in enterprises for AI. For TabNet, tabular data learning, we have seen a lot of applications in finance industry, for example, detecting financial crime cases, or like loan credit modeling or forecasting of different financial instruments and so on. Or healthcare, such as disease diagnosis from the sensor data measurements, or from tech industry for modeling of the user behaviors or predictions of the user purchases and so on. And tabular data use cases can be very diverse. They can be very different in data set sizes, complexity, and so on. And we have demonstrated success with a wide range of use cases. And for TFT, time series forecasting, typically the structured data problems are casted as time series forecasting problems, and there's a desire to model a sequence, and then we are predicting multiple time steps into the future. And especially for application areas where we need to plan the future, as in retail, like most retailers are interested in predicting the demand so that they can optimize their supply chain, or they can optimize their pricing and stuff like that. Or energy companies are trying to predict the demand so that they can optimize the energy distribution, or logistic companies. So these are some of the high value use cases that we have observed and we have shown good results with.
Okay, I have another question from the audience, and I think we should close it down. When deciding how much to consider rule versus decisions made by AI, is this formed from human input or AI will decide this, or does it depend on the use case?
Can you repeat the first part again?
Yeah, sure. When deciding how much to consider rule versus decisions made by AI,
Yeah.
is this from a human input or AI will decide this, or does it depend on the
Yeah,
use case or situation?
Yeah, so it's a great question. One of the areas we focus on is also how to have humans in the loop for the AI system deployments, because like especially for the cases where AI replaces some of the human tasks, it's important that AI outputs are highly confident and they are likely to be correct. And the AI system is not very confident about its decision, we need to have some humans in the loop. So there are certain trade-offs there. Like obviously we want to rely on AI as much as possible while having some like accuracy, safety, responsibility goals. And figuring that out, like how to efficiently use humans without taking a lot of time of theirs, and how to use the human feedback in improving the AI models, and how to basically make them work together towards some certain goal. So these are very important areas, and I believe that these will be much more important as AI is being deployed widespread.
Very well. I believe we have no more questions from the audience. So we have a short break right now, and then we'll have the final presentation for today's conference and the day following. So Sercan, I would like to thank you a lot for your contributions today. We have a little picture from you that will be sent to your home as part of your contribution to the conference. So thank you very much for sharing your ideas today. I think for my key takeaways, might be interesting to share some of Google's insights and what you just shared in your presentation for today's conclusion of the event. So thank you a lot, and we'll have a short break right now.
Thank you.
Yeah,
Thanks
thank you for being here today.